Hi, and today I'm going to be discussing math in the desert, specifically the Great Pyramid of Giza. And to demonstrate how it involves math, we're going to discuss the geometric construction and how it involves two well-known mathematical constants. We're going to be discussing pi and phi and how they are involved in the building of the pyramid. So when we talk about this pyramid, let's draw a pyramid just to give you guys a visual representation. Obviously, it's going to have a height and a width, right? This height is going to equal 280, and the width is going to equal 440. Now, obviously, what are the units that they're using? Well, they are called cubits. They're written as CB. And to give you guys a representation of what a cubit really is, just to imagine in your head, 1 cubit is going to equal 0.5263 meters. And of course, now you're kind of wondering, okay, that's a little specific, it's just half a meter, but this is a number that can be represented in a different way. And the way we can represent this number is pi over 6. So 1 cubit is going to equal pi over 6 meters. So not only does this tell us, hey, well, cubits and meters are linked, right? But they're linked by a factor of pi. So we know that pi was sort of involved not only just with the pyramid itself, but its unit of measurement, right? But then you also ask the question, well, what about the meters? Well, meters weren't established at the time, right? It wasn't a concept, a well-known concept, but meters themselves are derived from the distance of the North Pole to the equator. That's how we were able to create meters. And that is based off knowledge of the circumference of the Earth. You need to understand what that is. And so when we see a relationship between their unit of measurement and meters, it suggests that the Egyptians were very aware of what the circumference of the Earth was. So they knew the radius, they knew the volume. So this knowledge about the dimensions of Earth, which was very ahead of their time, right? But we also see pi in another instance. So we see that they have this obvious ratio, right, of units of measurement. But now let's discuss the ratio of side lengths. What if we compare the width and the height? Well, if we compare the width and the height using our givens, right, 440 over 280, if we simplify this, it's going to equal 11 over 7. Well, now let's talk about some pi a little bit, right? It's kind of the whole point of my discussion right now, pi. Well, pi is irrational, right? We can't just 3.1415 whatever, you know, like. So when we have pi, right, we can represent it. There's only one way to really represent it in an integer form. That's just an approximation. But we can sort of say that it's roughly 22 divided by 7. And look what we see here. This and that is, if we multiply by 1/2 times that, we'll get that 11 over 7. So when we look at the width and the height, the ratio of that, the width and the height actually have a ratio of pi over 2. And so not only do we see pi over 2 in just the units of measurement, but we see pi over 2 in the actual ratio of the lengths and the dimensions of the pyramid. So this shows us that pi over 2 is obviously or not pi over 2, but just pi in general was very involved when they were building the pyramids. So now that we've discussed pi a little bit, let's talk about phi. Well, phi is the golden ratio. It has a unique quality, which I will discuss right now. Phi is the only number where phi plus 1 is going to equal phi squared, right? So we have this equation. What can we do with this? Well, there's a very well-known theorem, right, that exists out there that the Egyptians weren't even aware of, right? I mean, this theorem was thousands of years later, and it's known as the Pythagorean theorem. So a squared plus b squared equals c squared. We all know and love it. But they weren't aware of it, but they used it. And let me show you how. This theorem tells us that we can construct a triangle, a right triangle specifically. So let's do that using this idea. So if we draw a triangle, right angle has a hypotenuse of 5, a leg of square root of 5, and a leg of 1. Well, what does this triangle even mean? Let's build another one identical to it, and let's put them together. Let's see what happens. Draw a bigger triangle, right? Right angles. We have 5, 1, and 1. So this whole thing here is 2, right? And we know that the height is going to be the square root of 5, right? Based off that triangle, we just built 2 triangles together. But why don't we do the same thing we did in the first example and compare the width and the height? So we make a ratio of the width to the height. Well, let's use our values. 2, so that's going to be 2 and the square root of 5. Well, what is 2 divided by the square root of 5 even equal? This value is actually equal to 5 over 2. So we know that their side lengths share the same ratio of the pyramid and this golden triangle, which is a triangle based off the golden ratio, right? But why don't we look at the angle as well? So let's call this angle here alpha. Let's do sine of alpha, right? We know the height, we know the side lengths, we can do some trigonometry. That's equal to the square root of 5 all over 5. And with the use of a calculator and sine inverse, we get that alpha is equal to 51.85 degrees. And that is not only the angle that corresponds to the golden triangle, but is the exact angle that the pyramid, it's known as the slope angle of the Great Pyramid of Giza. So we've seen a lot of how pi and phi, and even in this equation and triangle here, we see that pi and phi are linked together. And so when we discuss these numbers, it obviously, when we talk about the golden ratio, it's very prevalent in our world. It's actually, we can see it even in human geometry, the way we're built. So it begs the question of why did they choose phi in the first place? Why choose the golden ratio to base this pyramid off of? And to that, we'll never know why. It's a question that will forever remain unanswered. And that is my take on math in the desert.